Thanks so much. So I guess the core message that I would like to convey today is that compilation needs to be done with care. You can't just have a streaming compiler that kind of does the simplest possible thing and think that that really characterizes the limits of the performance of the code. That's one. The other is we all should work together because it's just much more fun that way. So if you have a look at the TQEC group, which grew out of a talk at this forum 2 years ago, so we celebrate our second birthday today, we have a lot of people coding together. The group itself has over 1,000 members now. So if you're not part of it, please join. And we welcome everyone from everywhere. If you have a look through this list, there's Jose Bolanos. He is actually a political economist by trade and got interested in quantum computing, learned how to code, and has done great work. We have Angela. She is by trade an attorney who specializes in Spanish bankruptcy law. So if you ever needed proof that anyone can do quantum computing, including something as seemingly impossible as topological quantum error correction, the TQEC group is there for you, right? You can do it too. So let's try to prove that today. So my goal is for this talk, despite the nature of its subject matter, to be possible to understand. So if I say something that doesn't meet that bar, stick up your hand, jump up, and I will answer as we go. I am not trying to lose you here. I want to take you with me. So what do we want to do? We want to leverage all of the work that the community has done. So as you are well aware, there are many, many, many tools that will take as input some description of a quantum algorithm and spit out gates. A small selection of them are on this page. I apologize if your tool is not here. It's only because there's not infinite space on the slide, not because I don't like your tool. You know, our goal is to make sure that TQEC has examples from every tool. So if you have not joined the TQEC group, do so. If you have a tool that you would like people to use, create an example and put it in the TQEC docs, right? We have space for your tool too. The goal then is to get it to compile down to one of two things. Maybe OpenChasm next, if you already have an export to that, or if you can go directly into PhysiX, that would be the goal. And we'll talk about what PhysiX is if you've never heard about it before. It essentially is a way of taking a quantum circuit and turning it into a graph. We'll go into some details. The next thing we want to do is we want to lay out that graph in 3D. And again, if you haven't seen diagrams like this before, we'll talk about it. But this is a representation of a quantum program. They're a lot of fun to play around with. One of the core tenets of the TQEC group is that if all you know is programming, then we can set you up with geometric problems, right? There are lots of problems where you don't need physics. You don't need to know what quantum mechanics is. You don't need to know what the surface code is or operators or stabilizers or any of it. It's just a geometric problem. It has algorithms that need to be investigated. Have fun, play, all right? And once we have those geometric structures, there's certain flows through those structures that determine what computation that structure is even doing. So you have to go and find those. Once you have them, you can then use standard tools to simulate them. And so we're going to take you on that full journey from an algorithm all the way through graphs to structures to correlation surfaces to simulation. And hopefully some part of that looks interesting to you and you reach out and we'll do some great work together. So here's an example. It's not a very complicated algorithm. This prepares a 7-qubit Steen code logical zero, all right? It's made of a bunch of simple gates and we want to show in detail what it really means to compile this properly, not to lay out 8 logical qubits on some array and then do it gate by gate by gate. That's a way to compile it, but it's not a good way to compile it. So what does good compilation look like? To do that, first we need to make sure we're all on the same page with what a CNOT gate is and what a Hadamard gate is. And while you may think you already know, we want to make sure that we use a picture that will help us do compilation. And the picture that we want is a CNOT gate is a map of operators. We don't care about the fact that it flips the target if the control is 1. That's not helpful. What we do care is that you can construct circuit identities where I put in an identity gate. 2 CNOTs cancel each other out. Then I multiply all these together and I see that a C0 gate is in fact the thing that maps a bit flip on the control to bit flips on both outputs, and so on. A bit flip on the target goes straight through, phase flips go straight through the control, a phase flip on the target gets mapped to phase flips on both. This is an equivalent way to look at a C0 gate. You can see that it's true from the circuit identities, and it is much more useful for compilation, so that's what we're going to use. Similarly, a Hadamard gate is the gate that changes bit flips into phase flips and vice versa. So any process, logical or otherwise, that does these things, maps operators in these manners, is this gate. We're going to see some pretty weird objects that do these things, and you'll be able to conclude, okay, well, it does the right work. It must be that gate. So, the surface code. What is it? Again, if you're not familiar, all you really need to remember is that you have some red squares. They detect phase errors. You have some blue squares. They detect bit flip errors. All right? So if we are looking for a qubit, what you do is you say, all right, there is a qubit on every one of these corners. So there are d qubits on one of these edges, d by d. In this case, this is a distance 5, 25 data qubits. If you bothered to count, you would find there are 24 of these plaquettes that look for errors, 24 constraints. There's one left over. There's a logical qubit hiding there somewhere. So it must be possible to flip the data both bit flip and phase flip. And you can do that. I said that these things detect errors. This blue square detects bit flip errors, but it only detects odd numbers. So if I put 2 bit flips on its edge, it sees nothing. And this chain of bit flips, therefore, is undetectable and changes at the underlying data. It's a logical operator. Now, what's the key takeaway? The only thing you need to know about this structure is that if we use this color code, RGB equals XYZ, and I apologize for the Z, but I'm Australian and I'm adamant that's how I'm going to say it forever. Anyway, it rhymes better as an American, but I don't care. Now, if you take this logical operator, it must terminate on a boundary of the same color. For example, if I tried to terminate my chain of X's on this boundary, well, then this check, this blue check which finds bit flips, is going to see it. It's not going to be hidden. So all we need to know is that logical operators of the same color stick to boundaries of the same color. And in particular, if we come over to here, it means if I have a logical X from this boundary to this boundary, it will stick and drag all the way through and not change. Logical X in is logical X out. Logical Z, blue to blue, in is logical Z out. Nothing has changed, therefore this is an identity gate. Notationally, the way we represent these things is, well, this block, slice by slice, is this quantum circuit. This picture is fundamentally just a quantum circuit. It's a quantum circuit that measures certain things such that bit flips and phase flips are detected. The details don't matter for the purpose of this talk. But what we do care about in this talk are we have D rounds of it. So this is sort of a D by D by D block. D in space, D in time, meaning rounds of this circuit. And then this thing is just for us because we're human. It actually is not there. It is just a visual spacer. So what really is happening is the software says, do D rounds of surface code error detection, la 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 la, I'm not actually here. Do another D rounds of surface code error detection and continue. So this is 2 D rounds of error detection. Why do we have those spacer blocks? So that when we have an identity gate that looks like this, and I hope no matter what your background is, you can recognize this as an identity gate. You play a game, red to red, my operators drag all the way through. Blue to blue drags all the way through. It doesn't change the operators, it is just an identity gate. And too often, even to this day in 2025, I see people laying out a forest of logical qubits and forgetting that if I want the data over here and there's something in the way, I can just do this. And this is a perfectly good identity gate. Surface code can do that, no problem. You can in fact do this in any code. This is just a very graphic visual representation of it. All right, so we've learned how to do nothing in the surface code. Awesome. Now let's have a think about how we do something. Well, something happens every time you have a junction. If it's just a piece of spaghetti with no junctions, that's an identity. As soon as we have junctions, well, let's have a look what it does. First, a definition. So we've colored our objects so that blue is Z and red is X. But right now, all that we care about is the definition of a blue node. It's the one where you have exactly two disjoint pieces of the same color. So I have blue on the front, blue on the back, two pieces, that's a blue node. Red on the front, red on the back, two lots of red, that's a red node. What are the properties? So let's imagine we have a red logical operator, which is X, doesn't matter really, just think about colors, an X logical operator, red logical operator coming in on the left. What happens when it hits here? Well, it can kind of stick to this wall and go down to here, but eventually it's going to hit this side, and what you'll find is that it splits. So you end up with a red line going up, this way, and this way. So there's a rule that if a logical operator of the opposite color hits a node, it propagates to all of the outputs. If the logical operator has the same color, well, I can drag blue straight through. I could also come around here and go back down the top. So it's not that if it's the same color, it must always hit two edges. If it's the same color, it must always hit an even number of edges. And again, this one slide in isolation is a good example of how the TQEC group works, because you could look at this object completely in isolation from anything else and say, okay, we have some rules. Cool, I'm a programmer, I get it. Now what do you want to do with that? Well, I want to represent those rules more simply. So firstly, instead of writing a three-dimensional object, I'm going to write those rules as just blue and red nodes and really graphically show same color, even number of edges, different color, every. Same color, even number of edges, different color, every. All right, so we can codify everything that we've talked about before in just some very, very simple graph rules. All right, so what can we do with simple graph rules? Well, we can analyze this graph and we can go opposite color, every, same color, two edges, and we can see that this graph maps an X on what will turn out to be the control of a controlled NOT gate to both outputs. Same color, even, goes straight through, different color, every, same color, even. Simple graph rules that show that a structure of this form, a blue node connected to a red node, is a CNOT gate. So what does that look like in structure? Well, it can look like whatever you want. There's not one CNOT gate. There's just a structure that it must be a blue node connected to a red node. This is a CNOT gate. No matter how this piece of spaghetti goes, it's still a CNOT gate. This is also a CNOT gate. It does not matter that it's turned sideways. It does not matter that you don't really know which one's the input and the output. It doesn't matter if time goes down. It's just the graph relationship that matters. This is a CNOT gate. You can take any Clifford computation and deform it in any direction you want, so you can implement it in amortized zero-wall time. And this is, again, a common property of every error correction code. It just happens to be visually very in your face in the surface code. Let's have some more fun. So I've taken away color just to make sure it's clear it's for either color. So it doesn't matter whether this was a red or a blue node. The point is you can topologically deform these things. So I can take this chimney and just drag it to the left, all right? And what I've done is I've essentially taken two nodes of the same color connected by an edge and merged them together. So we've just represented this graphically down here. Again, these are simple rules. You don't need to know that it's a quantum computer to say, okay, spider rule, graph, thanks. There's one more piece that we want. We want to be able to have a layer of Hadamard gates. Now, we mentioned in an earlier slide that one Hadamard gate takes X in and spits Z out. Well, an entire layer of Hadamard gates takes logical X in and spits logical Z out. So I can represent this as sort of a bath ring on my object that changes the colors and reduce that to a graph that does exactly the same thing. So if I had a red edge come in here, it would come out as blue. Couple more rules that we want, just to consolidate everything. So, you know, you can arrange these Hadamards around a node of a particular color, and since it changes the color going in, it basically changes the color of that node and allows you to remove those Hadamard gates. So that's, again, just a simplification rule. And last but not least, there is an identity rule, which basically, if you look at this rule here and delete the top and bottom edges, what you'll see is that regardless of the color, you go straight through. So delete the top and bottom edges, regardless of the color, you go straight through. So a node of any color that has exactly 2 edges is really the identity. You don't care about the color, you can just delete the node. Now, what are we going to do with all of those rules and graphs? Well, we're going to take this algorithm and we're going to turn it gate by gate into a graph. Every one of these initializations will be a node. The Hadamard will be that little box. These C-naughts will be blue nodes connected to red nodes. And here it is. All right? So it's the exact same circuit now written as a graph, where we have clear and simple rules to manipulate it. And what we're going to do is we're going to use the Hadamard rule to turn this into a blue node and remove the Hadamard. We're going to use the spider rule to merge all of those blue nodes together. We're going to use the spider rule to merge all of these red nodes together. And when we do that, you end up with this. So that huge algorithm becomes just this set of nodes. And then what we can do is play around with a simple graph. So I've translated it with one more rule. How do you prove this? You just send various colors in. If I send red in here, it splits both ways and comes straight out. Then if I send red in here, it would go along here. It hits the opposite color and goes out both ways. So despite the fact these two graphs are quite different, they map input logical operators to the same pattern of outputs. They do exactly the same thing. So if I see this anywhere in a graph or see this anywhere in the graph and want the other piece, I can just exchange them. And no, I haven't changed the computation. Why did I make that substitution? Because I played around with this graph for a long time and found that I could then map it to 3D node by node by node such that the total computation was small. We've had talks here talking about active volume. If you want to know the active volume of this, you just count the number of cubes. You'll find there are a dozen of them. So it takes just a dozen d by d by d cubes to realize several dozen gates on 8 qubits. Right. This is compilation done properly. It does not look like a forest of logical qubits with one gate at a time made into its fault-tolerant version. You leave an awful lot of optimization on the table when you do that, and it also calls into question a common comparison that is done in the literature. Go and take a forest of surface code memory and compare it to memory done in another code. Now, a computer is not supposed to do memory. It's supposed to do computation. If all you do is compare memory side by side, you really don't know whether a full algorithm is actually going to run well in that new code or not. So compilers are really, really important for this community. To assess whether an architecture is good, whether a code is good, you really must compile all the way and compile properly, actually going to a bit of effort. Otherwise, you can leave orders of magnitude on the table and you don't actually know whether your conclusion is correct or not. So you can do it by hand. We use SketchUp a lot in the community, do it by hand, or you can do it automatically. So this is an example of a piece of code written by a political economist who looked at the graph problem and decided, hey, that looks really fun. I'm going to work out how to turn that graph into these 3D structures. I get the rules, let's do it. All right, and he did. So he wrote a tool called Topologic, and that is in the process of being integrated and upgraded into the TQEC community as we speak. And you can just look at it node by node. Number 1 is a 4-way red node. It is here. Here is the 4-way red node. So you can go and check it. 1 is connected to 5, 1 is connected to 5, which is a 4-way blue node. Here it is. So that tool ran in a greedy manner, edge by edge by edge, laying it out, finding the closest place to put the next edge, all right? And as you can imagine, as a greedy algorithm, it's by far not the end of the story. It matters what graph you start with. It matters whether you allow a bit of flexibility when you place. It matters whether you look ahead a bit further and see whether the choices you are making now are going to block you in a bad way moving forward. There's vast scope to do this better, faster on bigger graphs, and it's a lot of fun. All right, so now what? We have a structure, right? We've used a political economist to take a graph and turn it into a structure. We want to now know what computation it did. So the computation, again, can be extracted with quite simple rules. As we mentioned, we have opposite color every, same color even. So we can feed various colors into these output nodes and just see what they end up, see how they branch and go out. Now, there is an aside that I want to do. Right now, we went from circuit to physics to structure, and now we're finding out what the computation does. Long term, that won't be good enough. Long term, we actually want to use the surfaces, these sort of pathways, these colored pathways that we got from physics, because those pathways also include information about time ordering. Now, we won't go into the details of that today, but just very briefly, for those that know, these dead-end nodes correspond to T-gates, non-Clifford nodes. And so if I have I'm just going to call it this colored line. It's a correlation surface. If I have a correlation surface that goes and touches earlier Clifford nodes, these non-Clifford nodes, these T-gates, have to be done first. So previously, with the map on the previous slide, we just took the whole structure and mapped it to 3D. We will need to add some additional constraints, such as time ordering, making sure that certain nodes, like this one, is placed in the structure later in time than other nodes. That's still work for the future. All right, so the algorithm that actually, for the moment, is adequate for our purposes and finds the correlation surfaces, with the caveat on the previous slide well taken into a point, is an efficient algorithm. But again, this is an area for future research. At the moment, it runs in complexity n to the fourth. If you're a computer science and you're looking at this and thinking, oh, I'm sure you can do better, well, come and do better. It should indeed be possible to do this in linear time. If you imagine looking at this diagram and working backwards, a long quantum algorithm is on a relatively small number of logical qubits compared to its depth. There is no reason you can't do the search using a sort of domain that sweeps systematically backwards through time. It should be possible to run an algorithm that runs in order n. Maybe you're the person that will find that algorithm. It definitely exists. So for the moment, though, this is the benchmark, and this is why we use an n to the fourth algorithm. It happens to be much quicker than the algorithm that is currently in physics. So this is a side-by-side comparison. Yet again, this is a slide saying there's work to be done. If you're curious about taking this algorithm and just getting it into physics, there's a nice atomic little piece of work. The code exists. There's a different code base that needs it. Help us do that. So moving on from there, once we have our correlation surfaces, what do we want to do next? Well, now we want to actually do some simulation. So it pays to a little pause here and remind ourselves what these things even are. So we have a graph, we have some colors on that graph, we have some rules, we've found them. But what do they really, really mean? In STIM, which we're going to use, STIM looks for sets of measurements that have a parity that should be deterministic if there were no errors. So these are the sets of measurements. Each one of these surfaces essentially sweeps through a quantum circuit and highlights certain measurements. It gives you the sets of measurements that will have an expected parity in the absence of errors. So they give us a way to check whether we have succeeded in our computation. Every one of the surfaces that we find must get the correct parity to have the computation work. So we can go and simulate those surfaces in STIM, those surfaces of measurements, and see if we did indeed get the parity we were supposed to get. And that looks like this. So TQEC will do all of this for you. You can start with an algorithm in your favorite tool, export it to whatever the usual save file is, and then import it into physics, and then topologic, and then TQEC, and then STIM. And the tool chain will take it through all of those steps and give you a simulation of your algorithm as a fault-tolerant implementation using the surface code and lattice surgery. So the goal is, of course, to keep going. This is not the end. This is just the current status as of about a week ago. We actually have updates even from the last week. So after I prepared and submitted these slides, one of the people who are working on this that I really want to call out. So Yiming Cheng is from China. He's one of our lead programmers, along with Adrian Cao, who's in the audience. has done a lot of work in the code base, and in particular tackled the rather nasty circuit that is preparing this state fault torrently in the surface code. So Craig Gidney published the seminal work on this. In principle, has given all the circuits to do it, but in practice, translating that circuit into a plug-and-play block that plays nicely with all the other blocks in TQEC is actually quite complicated. Why do I emphasize all of that language? The reason I do not work for Google anymore is because Google didn't want me to work with Yiming anymore. And I said, no. We will look into the legalities. We'll see if this is allowed versus export control. They refused, and then they fired me. But that is particularly why I'm standing here saying I am perfectly happy and we'll do it all over again. Talented people are needed and they exist all over the world, and it is ridiculous to deny interacting with them. You know, we need to work together as a community if we're going to build a quantum computer. In case you hadn't noticed, it is 31 years since Shor's algorithm was published. We do not have a large-scale fault-tolerant quantum computer. We have at best a few hundred qubits, and they're really not far enough below threshold to do anything useful. And we don't have any commercially useful algorithms, and there is no compiler for the surface code, and that's 31 years afterwards. And we have several hundred startups around the world working secretly. Now, anyone want to tell me that's optimal? We need to work together. We're all here to collaborate, so that's what we should do. There is no reason to do the same research 50 times over in 50 different labs, right? So Yiming has been hard at work doing this, has got it working. There are still some bugs, so this is like really bleeding edge what TQEC can do. But in certain situations, when you avoid the nasty edges, you can now put Y-basis initialization and measurement into TQEC, and it will do a full simulation of all of that. And as the user, it just feels like plug-and-play blocks. More. So I mentioned that topologic could be used to take a graph and map it to 3D. As of a week ago, it got a volume of 18 versus the best hand version, which was 12. But that doesn't mean people have sat on their hands. They've had a look and said, well, hang on, let's try to fiddle around with those graphs. Let's use that rule we saw on an earlier slide, this rule, and go and find instances of that in the graph, replace it, and then run that through topologic and do a search to see if you can get lower output volume. And you can. So as of now, the best automated search gets to a volume of 14, but there's still a gap to close on the best hand-created one, which is 12. And who knows, maybe the hand-created one is not the best possible. So again, this is a pure computer science problem, a fun computer science problem. And if it's appealing to you, join the group. There's plenty of room, plenty of PRs to review, issues to address, to tackle this problem. And again, I stress, remember what this used to be in terms of an algorithm. About a dozen CNOT gates, half a dozen Hadamards, initializations, measurements, all the way. This is what proper compilation looks like, and that's what we need to get good at doing. All right, future work. So at the moment, we've talked only about Clifford gates, Hadamard, CNOT, memory, and the S gate, which includes both Y-basis initialization and measurement. Moving forward, one of the things we need to do is replace the output. At the moment, we use STIM. STIM does not include feed forward. You can't tell STIM, this set of measurements is going to determine whether we do this set of gates later or not. So we need to upgrade the output of TQEC to be a format that allows us to say that. So that's, again, a very clear-cut project, another example of all the many things that anyone from anywhere can do if they just want to. Get the output in a different format. That allows you to specify feed forward. Why do we need feed forward? Because we want to do state cultivation, which may look like a really weird object, but it's not that complicated. You start with a very small patch of the computer and you try to prepare a T state. And then you check if it worked. And most of the time it doesn't. And so the termination of these little pyramids means we've checked, it didn't work, try again. The various points down here are multiple attempts to prepare a T state, which I stress is just this state done in parallel, until such time as one succeeds, and then you try to blow it up to the full-size surface code. And then you do another check to see whether you've succeeded with sufficient confidence. So what does that mean? When you decode, you try to get it right, and there is an opposite outcome that you try to avoid. It turns out you can decode both ways and see how close they are together. Very specifically, the decoding problem for the surface code looks like a constellation of dots that you link up by the shortest amount of pairs of string. So there's a weight to it, total amount of string. You can then go and ask it, well, what's the opposite possibility? If I instead say, my piece of string must touch a wall it didn't previously and match everything else, what's the total amount of string now? If those two amounts of string are close to each other, it means you don't actually know what you're doing, right? It means you're just guessing. If those two amounts of string are far apart, it means you're confident. You do know what you're doing. It's very unlikely it's the other thing to what you think it is. And so that means that when you do decoding in these blocks, you can decide whether you are confident you've got it right or you're not. And if you're not confident, you throw it away and you start again. So this is state cultivation. Attempt, do some local checks, throw away if they don't all pass. Think they did work? Great. Expand it to full service code, decoding, be a little bit more sophisticated now, not just succeed, but see how confident you are that you succeeded. If you're not confident enough, discard, start again. Anyway, this leads to very good suppression of error, so order p to the fifth. That is probably good enough forever. It certainly will be good enough initially, and as gates get better, it may be all you ever need to do. So we need to do this in TQEC with the feed forward to say this set of measurements determines whether we start again, and so on. Anyway, once that's done, that gives us universality properly with all of the details, nothing skipped. As a base case, you could sit there and say, well, leave enough vertical time such that the probability we do not get our T state is so low that we're happy to restart the computation if it fails. That gets away with needing to have probabilistic routing from a factory. You can just put a tower of a certain height and always route it in and discard the whole computation if it fails because you've made the tower high enough such that failure is rare. So we'll start with that. And again, this is fundamentally a paper with a particular circuit that needs to be coded up. It is not that easy, but at the same time, it does not require a PhD in physics to do that. You have to understand quantum circuits that already exist in code and get them into TQEC. So that is something we'll get onto. When that is done, we'll have our initial compiler. So what would it look like to have a fault-tolerant algorithm with Clifford and non-Clifford gates as well? Here is probably the simplest algorithm I can possibly imagine that you can't do on a classical computer cheaply from a theoretical point of view. Of course, you can do it cheaply. Simulating a single qubit's not that hard, but theoretically, it's not Clifford and therefore it's expensive. Alrighty, so what does this look like? This big stack, which we talked about on the previous slide, is preparing a T state. This is our input data. So this corresponds to this. All right. When we get to this point, there is a measurement that needs to occur. That measurement in the surface code is always a surface that starts somewhere and ends somewhere. So the surfaces of measurements we care about is a U shape that goes up here and down here. What does that measurement tell us? It tells us if we really got a T gate or we got a T dagger gate, because these things are always probabilistic in the surface code. Surface code T gates are 50-50 random T's or T daggers. If we get the wrong gate, maybe we wanted a T dagger gate, maybe we wanted a T gate, but if we get the one that we didn't want, we need to fix it. And we fix it by using an S gate, which, as we mentioned, starts with a Y basis initialization. And you choose whether this arm is patched into the computation by setting the basis of measurement here. A little arcane, but it happens to be that if this is an X or Z basis measurement, determines whether this is pruned off the structure or not. So in terms of time sequence, we wait until we have all of this information, all the measurements here, work out their corrected parity. So we send all of those measurements off to an external computer. It does its processing, it fixes them, it reports back to the parity. That tells us if we got the gate we wanted or not. And then and only then we tell this layer either do a layer of Hadamard gates and be measured in the X basis, or don't and be measured in the Z basis, because that will patch in the S gate to correct us if we did it wrong. So we can do all of this structure, the T, the H, the T, and the H, all of it in parallel. Time runs vertically. Everything happens at the same time, right? And this structure can go on arbitrarily, right? Great long algorithm with a layer of non-Clifford, a layer of Clifford, and a layer of non-Clifford, layer of Clifford. You can lay all of this out in constant time. And again, this is not a special property of the surface code. You can do this in any code of any kind whatsoever. It's a property of quantum computing. The rate at which you can do quantum computing is limited by how fast you can take a set of measurements, classically process what they mean, and you always have to process what they mean, and then based on the result, either do a feed-forward single qubit gate or not. Once that's done, the next surface, which looks like this, right? Previously I said, all right, great, here's my data, here's my U-shape. It tells me whether I got a T or T dagger gate. We'll have a look at this one. Here is my next T state. I want to know, did it do a T dagger or not? Well, let's follow the path. That path goes around, goes down here, goes back, goes around here, goes to the opposite color. So now instead of a blue logical operator that I'm dragging through here, I'm now dragging a red logical operator through here. The red logical operator hits blue, goes in both directions, all right? And right here, it's going to either go down here into the S, convert back into a Z logical operator, right? This supports Y surfaces, both X and Z. It will come back and go into this tower. The short answer meaning that whether or not I got a T or T dagger is unknown until such time as I have capped off this piece. So only then can the classical processing begin to tell me what I need to do on this next tower, which is deliberately that little bit taller to represent classical processing. Now, why would I emphasize all of that? Today I've talked about compiling to a 2D nearest neighbor architecture, which is certainly not the universal architecture. We've heard about ion traps, we've heard about neutral atoms. These are very exciting platforms. It is an often cited criticism of things like neutral atoms, and I mentioned earlier that I really like neutral atoms, that they are slow. Well, it doesn't have to be so. A neutral atom computer, just like the surface code represented in this picture, can implement everything in parallel in principle, given enough qubits, and qubits are really cheap in a neutral atom computer. And then all that matters, as I said, is how fast it can measure. Measurement is tens of microseconds in a neutral atom quantum computer. How fast it can do classical processing, that's uniform for all approaches, right? The only thing that makes classical processing slower is if your error rate is higher. The closer you are to the threshold, the harder the problem is. Both the more errors you need to deal with, and plus the problem itself fundamentally gets more difficult. But under the assumption that everyone has comparable error rates, the classical processing is the same difficulty for everyone. And then the feed forward, again, is electronics. It is not dependent on the quantum hardware. So in principle, a neutral atom quantum computer can process almost as fast as a superconducting processor can, despite the fact there are orders of magnitude difference in timescales between the gates in a superconducting architecture and the cooling in a neutral atom quantum computer. All of that processing can be done offline with enough qubits. So one other thing to take away from this picture is the concept of the output format. What does quantum software look like? Could, and in my mind, should be a geometric picture, right? Because this tells you what to do in an architecture-independent manner. You could then imagine feeding in additional hardware details to take each column of blocks, right? You could give a location on your 2D computer a column of blocks, and it would convert those into appropriate slices of circuit for the underlying hardware. All right, so in summary, TQEC is a group of enthusiasts, a true group of enthusiasts. We have people from all walks of life, from students, professors, and in particular, political economists and attorneys that do great work, all right? You can do it too. We make heavy emphasis on not burying people with endless learning to get to the point they can be productive. And I wasn't joking when I talked to other people. If people came to next Wednesday's group meeting, I will lay out problems that do not require you to know anything about the previous 2 years' history of coding that would allow you to get started, right? Quantum computing does not have to be some esoteric tower that hardly anyone can access and we all do it in secret. I mean, that's nonsense. We'll never get anything done if we do that. So come and join us. Let us show you how it should be done. Let's see what we can all do together. Thank you.
Thank you.